Thanks for being in my session. So my name is Torsten Strauß. I'm a consultant, trainer, and speaker from Germany. And I would like to present parallelism to you. So it's a little bit surprising that I have roughly maybe 60 people in the room, and I don't know how many people will attend online. But anyways, this is a very specific topic, and it is marked as an expert level. So maybe this was my fault. So the expectation seems to be very high. So hopefully everything works. Okay, cool. So one question, who has more than 10 years of SQL Server development experience or DBA experience here in the room? Oh, that's great. Okay, cool. Nice. Okay, I guess then you're in the right session. Okay, so what I have done in order to prepare the session is I created a few tables which I will use later on. So mainly 2 of them. And I mean, this is just, you will get the code, yeah? I need to find out where I can upload the code, but be sure you get it. So the final idea is that I have 2 tables here called Big Table 1 and Big Table 2. 1 second. This is so super annoying. You can see the definition. I mean, it's just to have some records, or some, to be precise, we will have 1 million records each. So we have a Big Table 1 and a Big Table 2, which is exactly a copy of the other one. Just to deal with a few more records than just AdventureWorks. Yeah? So I have another table with me, which have 500 million records, which I will use later on, just to give you a rough understanding about the data amount which we're using in the examples. Okay, so what is parallelism? So parallelism means that SQL Server can execute queries using multiple CPUs or cores at the same time. So that means when a query is executed, SQL Server can use more than one CPU to satisfy the query. So parallelism increases the overhead, which we will see, and I would say in the beginning already, it is not a very good idea to see parallel plans in an OLTP environment. When you have something like I would say, reporting system where you have millions of rows and you want to use column store indexes, it's definitely worth to have parallelism, but otherwise it is not a very good idea, as we will see. So again, when you have an OLTP system, you have a lot of possibilities to detect parallel plans, for example, query store, and it is definitely a good idea to tune them. Yes, so we would see something which is called a thread pool starvation. That is when, you know, that we have a maximum number of concurrent worker threads available in SQL Server depending on your CPU and architecture and so forth. And currently on my machine, I have 576, which you can overwrite, yeah? But it is not a very good idea to do so, because then in the end you will end up with a complete different queue. And so therefore, my recommendation is do not overwrite the maximum worker count, yeah, just to save some money, because it is CPU. CPU means license. Even in Azure, CPU is more costly. So that is what we will cover definitely, thread pool starvation, I think in the end, if I remember correctly. And this is very hard to resolve finally. So, and you can see the recommendation is use parallel query executions only when you have a small number of concurrent queries, which is not the case for OLTP systems, because in an OLTP system you usually have small number of concurrent, you have a big number of concurrent queries, and these queries are, I would say, the majority is very cheap. Yeah? That is the idea of having an OLTP system. Otherwise, you have a reporting system where everything is completely different. So let's go to the pre-requirements. As you can see, SQL Server must be running on a multi-processor, multi-core, or hyper-threaded machine. Otherwise, I mean, when you have just one core, there's no way to create or to execute a query in a parallel fashion. That doesn't work. So then we will cover something which is the processor affinity. So the processor affinity mask, maybe someone of you already used the affinity mask in the past. Maybe with good, maybe with bad examples. When you do it right, it is definitely worth to do. When you do it wrong, you will end up with a lot of performance issues. Yeah? So we will cover this. The maximum degree of parallelism, so this is a setting on an instance level. So this is an advanced configuration, but I don't care. Must be set to 0, which means SQL Server can use all available cores within one query, or for sure more than one. It is set to 1. There's no way that the query can, or that the engine can use more than one CPU or one core at the same time. So yes, the maximum configuration for resource governor must be also allow the use of parallel plans. I decided to skip resource governor because otherwise it is already hard to cover everything within 60 minutes. And when I now start to introduce resource governor to you with different queues and priority and something like this, I think it's nothing which I can cover in an hour. I can, but this is too much for you, I'm pretty sure. So, and for sure the last one is the estimated cost. And this is really want to emphasize this. When we deal with costs, this is always estimated. It is never ever the actual cost. You will not even see an actual cost of a query. Yeah? You will get something like, which is very close to the actual cost when you recompile your plan and your statistics are stale and not stale, when your statistics are maintained. Yeah? Then you get very, I would say, you get something which is very close to the actual cost. But you can see already the impact. When you have a stale statistics, the estimation is wrong. So therefore, SQL Server Engine will choose a parallel plan, maybe because of a complete wrong cost estimation. And this can completely screw up the performance on your system. Yeah? So that is something I really would like to emphasize. Make sure, even in Azure SQL database, yeah, that your statistics indexes are maintained. So I've seen a lot of SQL databases in Azure where people think they do not need to care about indexes, statistics maintenance, and so forth anymore, and the system is completely slow, yeah, and they wonder why. So one of the reasons is stale statistics and fragmented indexes. Okay, so I will start simple, hopefully. And first of all, let's dive into the pre-requirements. You can see there's one DMV. By the way, can you read it? Oh, yeah, that's okay for you? Okay, otherwise, I mean, the last row, I can even blow it up a little bit, but it works. So you can see I'm currently using my local machine, which is a laptop. For sure, I have only one CPU in my machine, but it is hyper-threaded. That means I can use more than one core, exactly, to be precise, 8. So the pre-requirement that a query can be executed in parallel is, at least from that perspective, guaranteed. Yeah? So we have 8 cores, so therefore SQL Server can use more than 8 cores. But as we will see, the maximum degree of parallelism and the number of cores is not similar to the maximum or to the used threads. As we will see later on, the shape of an execution plan will dictate the number of CPUs which are used in a query, which can be a multiple of 8. Yeah? So we will see, for example, that a merge join will use 3 branches. Therefore, we will end up with 24 threads already. And now take into consideration, my machine have only 576 maximum worker threads. So when you run something like this, a merge join in parallel and in a concurrent workload, it is very likely that the number of threads will be exhausted, and therefore you're running in a thread pool starvation, which is completely different for a hash join, as we will see, because the hash join have a blocking, also I would say a build, and a streaming, which is a probe phase. So therefore there will be only 2 branches. 2 multiplied with 8 is 16. So therefore we will end up with 1/3 more possible queries which can be executed in parallel comparing to the merge join. So what I want to make sure that everyone understands that the shape of an execution plan have an impact on the number of cores, and therefore the, how can I say, the availability of CPUs. Yeah? So that is something you can take into consideration. So I hope my session is not too bad, because the first one is already leaving. So bear with me, yeah. So please stay in the room, even if it's completely shit. Yeah. So, okay, parallelism. Yeah, maximum degree of parallelism. I already mentioned that. I'm pretty sure every one of us knows, or you knows, what maximum degree of parallelism is. Nevertheless, let me give you an example. You can configure the maximum degree of parallelism on instance level only, yeah, not on database level yet. I hope I don't know if it is possible, but you remember that Microsoft decided or implemented, sorry, one second. maximum degree of parallelism is available on an instance and database level. So what I was I mixed it up with cost threshold for parallelism. Sorry for that. So, which is a good, I would say, change, because now you can differentiate the maximum degree of parallelism on every single database, because usually you have a mixed workload. Maybe you have an instance where you have an OLTP database and you have another database in the same instance, which is more or less reporting. So therefore, it makes sense to separate the workload, to separate the databases, and therefore set the right maximum degree of parallelism on the appropriate database to make it work. Okay, so I didn't remember anymore if I executed this one already. Okay, that works. So and you can see we have a database scope configuration, which is set to 0, as well as on the instance level. That means SQL Server can now use all available vCores, right? There's no limitation, as mentioned already. Either it is 0 or it is set something which is more than 1. Otherwise, all queries will run in a serial fashion. Okay, so let me execute an execution plan. Let me execute a query and show you the execution plan. That is what I want to say. Let me do this. I mean, you will not see, I'm discarding the results here, because otherwise it takes longer just to see some rows. I'm not very interested in the rows. I'm more interested to show and share the ideas of the execution plan with you. So what you can see is, because DOP, also maximum degree of parallelism, the setting is set to 0, my machine can now use at least a factor or multiple of 8. Yeah? So in this, this execution plan will already give you a rough understanding about what happens here. So you can see the thread stats, so the thread reservation and the number of branches, and you can see the number of used threads. So currently this workload or this query is or used 8 concurrent threads at the same time. You can see that there's only one branch. We will talk about branches later on, but you can consider a branch like every branch which have a gather stream, some kind of a parallelism, an exchange parallelism operator. So you can see this is one branch, and therefore we have a factor of 1. 1 multiplied with 8 is 8 reserved and used threads. Okay, that is how it works. So let me go down. When I now change the system to 1, I mean, very likely you already understand what happens when I now use the execution plan another time, the query another time. So you can see this time your query is limited by just 1 vCore. Why? You can see this in the properties, which is sometimes very helpful to understand why. I cannot blow it up. I don't want to use this kind of zoom function because this completely annoys me. So I will read what you should, I will tell you what you should see there. Non-parallel plan reason is maximum degree of parallelism is set to 1. So this is by intention. So this is what we did. So you remember that we set the DOP setting to 1. You get the reason, because normally you expected that the query is running in parallel because the cost threshold of parallelism is set to 5, which is the default on my machine. But the estimated subtree cost is definitely more than 5. As you can see, it's 117. So therefore, we expected to see a parallel plan. Now you get an idea why SQL Server is not able to use a parallel plan. You limited the number of vCores which can be used by one query. Okay, cool. Let me go down. So what I have seen, for example, I have one customer who is running SAP on SQL Server, which is a little bit strange, but it works. Yeah. SAP is very smart. So what SAP did is they, on an instance level, on a database level, they set the maximum degree of parallelism to 1. That means every user query is by default running with just 1 vCore. But internally, they override the maximum degree of parallelism for every single query with a maximum degree of parallelism to, I don't know, 8 or 16 or whatever. Oh, sorry. This is what I didn't expect it. So that is very nice, because when you run a user query, you will wait, right? When SAP is executing internal queries super fast, and now the user will complain or complains about their user queries, which are slow. yeah, and now you have to tell the customer, okay, we can adjust the maximum degree of parallelism, yeah, the setting on an instance or database level, but then it is very likely that you're running in a thread pool starvation because you just have a limited number of maximum worker threads available. So that is always a balance, finding the right balance. That is the problem here. So again, now we are limited to 1. So you remember I set maximum degree of parallelism to 1. Yeah, that is the reason why this query was single-threaded. But for sure, I can overwrite the setting, and that is what, again, SAP does. Yeah? So for example, I'm pretty sure other application will do the same, yeah, to get the best out of your license, of your CPU. And when you do want to do something, okay, you have to pay more. So you can see this is now a parallel plan. You can see the double arrow, which indicates a parallel operator or iterator, depends which kind of lecture or which kind of books you're reading. I will call it operator. And so we are overwriting the maximum degree of parallelism by the query hint, which is sometimes exactly the right idea. So for sure, I can play with maximum degree of parallelism to override it. I can set it to 8, so on the instance level, but I can override the query hint. So it works from both ways, either from an instance level and a query hint, which is less, or higher than the maximum degree of parallelism, which is set on a database level. The database level, I mentioned that already. You have a maximum degree of parallelism on database and instance level. Database level will always overrule the instance level, which is okay. Yeah? Okay, let us go down because we still have a lot of things to cover, and this is easy. This is an expert session, so let me go down. So cost threshold for parallelism, I mean, I need to explain at least maximum degree of parallelism and cost threshold for parallelism, because otherwise maybe you will be lost later on. So this is still easy. But you can see this is the default. I mean, the default of 5 for cost threshold of parallelism is super old. It is older than 25 years. Microsoft decided in former days, so 25 years back, that it is a good idea when your query is running more than, in this time it was second. When it is running more than 5 seconds, please consider a parallel plan. Compare the cost threshold, compare the estimated subquery cost, and when you see, the engine sees, that the parallel plan is faster, likely faster than the serial plan, use a parallel plan. So in these days, this is definitely not 5 seconds anymore, because we all know that CPUs are much, much, much faster now. And now we can discuss, and we did a discussion, we had a discussion with Microsoft in an MVP, I don't know, call. We asked Microsoft, why 5? Why not 30? Why 50? And I mean, the answer is fine. Everything you put in here as a default is wrong, because it's completely depending on your workload. That means if you set it to 50, maybe it fits for 10 customers out of 100. If you set it to 5, maybe it also fits to 10 out of 100. So you need to find the right cost threshold for parallelism, depending on your workload. And that is hard. That is really hard to find the best cost threshold for parallelism. There are several, I would say, advices. I don't want to stick to an advice. I really want to dive into the workload, which you usually can do with Query Store, for example, or DMVs, wait stats, or whatever, to figure out if your machine is running faster or slower when you change the cost threshold for parallelism. Yeah? It's very, very, very difficult. Yeah? Therefore, I don't want to give any recommendation. I just want to recommend, give it a try. Change it, give it a try. Do some evaluation for, I don't know, for Fortnite or whatever. Afterwards, you can compare your queries in the Query Store, and maybe you will figure out that the query is running faster. The entire workload is running faster. It is not just one query, because otherwise you can always override the maximum degree of parallelism setting to force parallelism or to force a serial plan. So it's very hard when you have a workload. Yeah? So yeah, I mean, I don't want to go into detail here because this is very, very simple. So you have a serial plan, which usually costs, or in this case, it costs something about 29. By the way, there is no unit. It's a combination of I/O, memory, and CPUs. And therefore, there is no meaningful unit. You can call it euros, you can call it whatever. So it is just a factor. And it's only worth to compare the same query and figure out which kind of costs are less in order to get the better plan. To be honest with you, I never ever care about cost. I really don't care. The only measurement I'm looking for is the IOs. Yeah? So because this is something I can reduce by an index strategy or rewriting the query, cost is fine, but it is cost, yeah. So, and you can see as far as the serial plan, which is 29, is more than your cost threshold for parallelism is set to, which is currently 5, SQL Server will consider in a parallel plan, but there is no guarantee. There is no guarantee that a parallel plan will be chosen just because a parallel plan will be cheaper, because sometimes some of the operator they will use in your query execution plan cannot be parallelized, cannot run in parallel. Yeah, so it's impossible. So and that is why sometimes you expect to see a parallel plan, but finally you see a serial plan. Yeah, for one good reason. You can see, for example, which is very interesting, I would say, at least for me. I hope you will find it interesting as well. Yeah. Otherwise, please stay in the room. So I have one query which is a little bit more complicated to compile, and you understand why. The more joins, for example, I use in a query, the more complex it will be to find the best plan. Because you can either join table A with table B first, or table B with table A, or you can join another table, because you can see the more joins I have, the more alternatives I have. So all these kind of alternatives are saved in a so-called memo structure, which is an in-memory object, which will be used in order to compare the estimated costs. But there's cost for compilation, which is CPU cycles. Yeah? So this is CPU and a little bit of memory, as mentioned, because it takes, at least the memo structure have to be kept in memory. So when I execute a query like this, you can see, I can blow it up a bit. Yes, that works. This is so super annoying to find the point where I can blow it up here. Anyway, so you can see with a specific trace flag, which I set here in the end, which is 8675, you get the net cost CPU cycle and time for different exploration phases. So when the query engine or the query optimizer have 3 phases, you can see them. Search phase 0 is it's a very simple approach, right? Mainly for OLTP queries. This is not an OLTP query anymore. So, and because the cost which is allocated to the search phase, which is 25, yeah, roughly 25, is still higher than your cost threshold for parallelism, SQL Server now considers the search phase 1 and it will apply more algorithms, more rules in order to find a better plan. So we can see finally the plan, or the shape of the plan which was selected by search phase 1 within a given time, because otherwise you have to wait forever to get the best possible plan. We will never ever have the guarantee that there is a SQL Server engine selects the best plan. It is called the what is it called? Best plan. The optimal plan. It is called best plan found. Yeah? So within the time, this is the best plan SQL Server can find. Otherwise, it has to spend more and more CPU cycles, more and more time just to find the best plan. So the user have to wait. And finally, only the query takes a few milliseconds to run, but the user waited more than, I don't know, 5 seconds to get an execution plan. So you can see, because the cost is still too high, SQL Server considers search phase 2, more and more algorithm, and in search phase 2, it's the first time that SQL Server considers parallelism. So, and you can see finally, SQL Server takes this plan. I mean, for this query, right? And this is limited to 1. You can see it here, 1. That is the reason why the search phase 2 here is used only once. You can see search phase 0, 1, and 2. Now let's try to figure out the compilation time of this query, or for this query, for the execution plan, right? So I cannot promise, so 13 milliseconds, you can see it here, 13 milliseconds, or nanoseconds, sorry, to find the best plan within a given time, which is definitely fine. It's a good balance between execution time and CPU time and compile time, because within the CPU time, there is compile time and the time a thread will spend on the CPU. And everything else is execution time, which is nothing else than the mentioned CPU plus wait time. Yeah? SQL Server have to wait for resources. I don't know, for a block, log, for memory or whatever. So when I now run the same query another time, but this time I don't limit, by the way, it's a little bit too big for me. Still okay? Okay, cool. This time I run the query another time, but not with the hint of maximum degree of parallelism set to 1. That means SQL Server now can consider parallelism. That means when we go to the messages, and I have to blow it up another time, you can see that the search phase 1 and search phase 1 was one which was used during for considering parallelism, but everything else is completely true. So you can see that search phase 1 is iterated 2 times. One for the serial plan, another time for the parallel plan. And you can see that this is a serial plan about 9.5. This is the parallel plan, which is 8.8. So that is why SQL Server finally takes the parallel plan, because it is definitely cheaper. But this is not for free. 1 second. I hope it works. Sometimes it is mixed up, but before we had 13. This time we have 19 at least. We spent we spent 6 nanoseconds more to find the parallel plan, because there's always search phase 1 for the serial plan and another iteration for the parallel plan. That means we will end up with more CPU cycles. Okay, I mean the query is definitely still very simple, but when you run more and more complex queries, the compilation time can be definitely much higher than 19. There are internal thresholds, as I mentioned already, so there is a limit, but still it is definitely worth to. There's specific DMVs. I don't want to go into detail here, but you understand that this is nothing is for free. So, processor affinity. As mentioned already, SQL Server can use by default all the CPUs which are currently visible for SQL Server. And the visibility is set by the affinity mask. So, for example, when you go here and go to properties, this is a GUI processors here. This is what I'm talking about. Yeah, I mean, you can set it. And I have one NUMA. We will talk about NUMA in maybe 5 minutes. So within one logical NUMA, or it is not a logical, it's even a physical NUMA, we have 8 cores. Okay, so SQL Server can use all of the cores. Okay, I will tell you what a customer of mine did, and I know that there's more than just this customer. They did the following. So they set the processor affinity mask to auto. So that's by default. Okay, and now they use something like this. Maximum degree of parallelism is set to 0. MAXDOP is set to 0. That means SQL Server can use 8 cores. Okay, on my machine. Let me go down. So this time I will set the cost threshold for parallelism to 50, which is a little bit higher than 10 times higher than the default. Yeah, so just want to check everything works. Perfect. So when I now execute this query, and I will do it in another session, because otherwise I will end up with a mess. I will use a complete different one, that one. And we will open the resource monitor. You can see on the right-hand side the CPU, the physical CPU, which contains 8 cores. Yeah? Currently almost idle. So let me execute this one, and we will see what happens. It's a very costly query in terms of the number of records which I get. You can see that almost every single core, it's some kind of a balanced workload. You can see all the cores are sometimes or some kind of busy. Yeah? Sometimes CPU 2, for example, is a little bit more idle, but you can see in general all the CPUs are busy. Okay, that is, SQL Server does not have a thread allocation to the CPU. There is no, how can I say, there is no direct boundary. That means you know that the query which I run is in a serial fashion. You can see it here. It is set to 1, but even though SQL Server can internally use all the CPUs which are visible for SQL Server. That means the workload is balanced. You can see the peak here, right? So that means even if you set the maximum degree of parallelism to 1, SQL Server will not use just 1 core. Instead, it will use 8 cores, because there is no relationship between the so-called scheduler, which is a logical component, and the physical core. Okay? So let me do this another time, and I was too slow. That is the reason why I want to do it another time. That is the session number 51. Let me execute this another time. And what I want to see here is, or what we will see here is, the processor affinity. So that means the current workload, you can see the statement here, and for sure the execution plan, a lot of more information, which are very useful, but not for this presentation. You can see the affinity mask is set to 255, which means it is a bit mask. And you can see already how it works. I mean, 8 cores, 1, 1, 1, 1, 1, 1, 1, 1, which is 25. That means at 250 and 5. That means all the cores can be used by a single threaded query. But the schedulers will move across the CPUs in order to have some kind of a concurrent balance between the CPUs, or cores, to be precise, which is often good. Yeah, the drawback of this is context switching, because CPUs have to load data into the cache, and then they will discard everything, and then with the next cycle they will load another time. It has some overhead, but it is, in most of the times, I would say, the best option. Let me do this. I have another query here, which have 2 branches. As I already mentioned, let me open that one. Let me execute this query, just from a query perspective. Okay, so you cannot, I need to execute the query to see the branches. I don't want to do it because it takes some time, yeah, by intention, because otherwise I cannot monitor the workload in the background. Let me execute this one. So this is session still 51. Let me execute this one. So when we now open, so this is not a single threaded query. Instead, it is using more than one CPU. This time we can see that all the CPUs are much more busy, because the query itself is much more CPU intensive. But again, SQL Server can use all cores. And this time because we have more than one thread, a thread is allocated to the specific CPU or vCore. So when I execute the query another time, because I'm pretty sure I was too slow, the query was too fast for me. Let me do this. We can see that this time, shit. Is this done already? No, okay, I was too slow. Okay. This time we can see that there is not just one thread allocated. Instead, there are 17 threads allocated. Maybe you expect to see 16 because of the number of branches, and the requested DOP branch multiplied with 8 is 16. That is the reason why we can see 16 threads plus 1, which is the so-called coordinator thread. We will talk about coordinator thread in a minute, or maybe 5. So this is the coordination of a parallel work. That is the overhead, right? There has to be one thread which coordinates the work, because the other threads are working completely independently. And there's a gather stream to merge all the work from 16 concurrent threads. That is the coordinator thread. So let me do this. 1 second, let me scroll down. Yes, so now the customer did the following. They read a blog article, and there was a recommendation to use a processor affinity mask for whatever reason. I mean, reading blog articles is definitely fine, but you have to understand what you're reading, and you have to give it a try. And the customer tried, but they failed, but they didn't understand why the performance was so slow. What they did is they set a processor affinity mask, processor affinity, yeah, which means SQL Server can have, or they are only, in my example, yeah, this is my machine, I don't have a VM with me. But you can see I limit the CPU, the usage, and the visibility of the schedulers to 2. That means SQL Server has only visibility to 2 cores. The intention of the customer was, okay, you have reporting services running on a machine or another services which are already CPU intensive, and they want to give a dedicated CPU to the SQL Server and dedicated CPU to all the other services, which doesn't work, because SQL Server can be limited by the number of CPUs which are visible, but all the other services not. That means this is now a problem, because you limit SQL Server by just using 2 cores. So let's see what happens. So there is a DMV which is called DMO schedulers. OS is operational system. That already indicates that the scheduler is nothing else than a logical object on a scheduler, on the Windows host. We can see that there are only 2 visible cores, right? So SQL Server knows or does not know that more than 2 cores exists. That means every single query you will run now can only use 2 cores. Okay, let me go down and I will show you the problem now. So when I execute this query, this is single-threaded, as you can see. Same example as before, exactly the same, but this time a visibility of 2 cores. So you remember the first time that SQL Server was, or the engine was able to cycle across the CPUs, even the maximum degree of parallelism was set to 1. All the CPUs were busy, not very busy, but they were busy. This time what happens is, when you execute this workload, only CPU 2 becomes busy because the maximum degree of parallelism is set to 1, only 2 vCores are visible, and now the problem starts. SQL Server cannot cycle across the vCores anymore, the logical schedulers. Instead, the CPU is forever related with the thread. That means, now you can think what happens. When you have a CPU contention, in this example of CPU, when you run, for example, something like the CPU stress, where you do something like, you can define an affinity mask, right? And you can activate this. I don't want to do it because otherwise it takes too much time. CPU 2 becomes busy. So now the problem is, when CPU is already busy by the system, by the service or whatever, and you run something like this, and the CPU cannot, or the scheduler cannot move across the CPUs anymore, what happens? You have a contention on your CPU. So that is the worst case ever. So hard to figure out the problem, easy to resolve. How can you resolve it? There are 2 options. Either go back to the affinity mask, set it to the default. Second one is to enable trace flag 8002. That means when you enable this trace flag, SQL Server still only sees 2 vCores and can only use 2 vCores from a thread perspective, but can still use or move the logical schedulers across the CPUs, which is not a contention. I mean, it is not very likely that you run in a contention anymore, because for sure, you can balance the workload across more than 2 cores, but 2 cores will be busy at the same time only. That is what you are telling SQL Server here. Okay, I will skip that one. Housekeeping is always fine. Just want to make sure that everything works perfect, and hopefully this is deactivated. Yeah, okay, cool. It was never ever activated. Okay, let's talk about NUMA. When we talk about parallelism, we need to talk about NUMA. So NUMA is nothing else than this one. It's a CPU architecture which is very common. You can see in this case we have 4 vCores. We have 4 vCores, and the problem is the following. As far as a vCore belongs to the same physical CPU, all the data which will be shared across the vCores can be shared within the cache, which means it's super fast. When you set a maximum degree of parallelism to 16 to 0, and you have 16 vCores available, what happens now? When you have 8 vCores per CPU, it means you have 2 physical NUMAs and you have 2 physical cores. Then SQL Server will exchange data between the vCores or between the NUMA nodes, which is extremely slow because this is a bus. This is not the internal cache which can be used. That is why you should always set the maximum degree of parallelism to the number of cores within your NUMA. There's a formula which changes every time. There's a limit. I think it is currently 16. Even if you have more vCores than 16 within NUMA, yeah, go with 16. But if I remember correctly, SQL Server introduced soft NUMA nodes, which means it will automatically detect the available vCores within the NUMA and will reduce the NUMA, but still your setting matters. The problem is, there is a latency between the vCores. So, within the vCores within two NUMA nodes. This was something I did for a machine which have more than two physical CPUs and therefore more than two logical NUMAs. This cannot work on my machine because, you know, I have only one CPU here, but you can see the latency. We have, hopefully you can see it, we have 30% of latency when we need to exchange data between NUMA 0 and NUMA 1. That is already a bottleneck from a CPU perspective, from your host perspective. So you're wasting a lot of CPU cycles for nothing because you are exchanging data. So that is something you need to take into consideration. That is the reason why you should always use or set your maximum degree of parallelism. So what I did is the following. I executed a query like this. So a very simple one, and you remember this query already, with different MAXDOP settings, with 1, with 2, up to 8. And I measured the time, CPU time and all the weight stats which are related to this query with the different options. So this is a result. It's very interesting to see because most people think, oh, this is an OLTP workload. It is not a reporting system. Yeah? What you can see here is when the number of cores increases, that means SQL Server is allowed to use more and more cores for the same query, the execution time, this is the execution time, goes up. This is completely the other way around, you might think. Why? On the right-hand side, you can see why. CXPacket, which is class exchange packet, I hope we can cover this, at least for a few minutes. This is the overhead of the coordination for parallelism. You can imagine that it is much more complicated to coordinate different threads which are not knowing each other than have it running the same query in a serial fashion. That is what you can see here. CXPacket is increasing over time. So the more vCores you add, the more threads you add to your query, the more CXPacket you have, and you remember that execution time is nothing else than CPU time plus wait time. That means you're waiting for the coordination of the query which is currently running in parallel. It is running more and more in parallel the more threads you add. That is why an OLTP query, very likely, the performance will go down, not up. So now the trouble begins. You need to think about the right DOP setting, the right cost threshold for parallelism, and you need to figure out which queries will benefit from parallelism and which queries, why is this always happens here, and which query will not benefit from parallelism. But this is already a good indication. So when you run something like this, for example, and I want to reconnect to get a new session. So we have session 55 now. So let's see what happens when I execute a query like this. This is not limited. You can see it is not limited currently. And oops. I'm working in master. Sorry. Yeah. I need to be very, very fast. Okay, cool. You can see what happens. This is waiting task. So, or to be very precise, this is on, okay, I don't need to be fast because session wait stats are recorded until the session is gone. That was a reason why I especially opened a new query or new session. You can see why the query is running slow, because of CXPacket, right? So the query was allowed to run with more than one thread. So let's do it. And let's figure out the execution plan. Yeah, more than one thread. Even we see a hash match here. So we have two branches, one branch, another branch, but this can be reused by this branch. So therefore we have only two branches. As I already mentioned, this is depending on the shape of the execution plan. Hash match has a build and a probe phase. A build is blocking, probe is streaming. That is the reason why one of the threads can be reused. Completely different to a merge join. Okay? So that is the reason why your query is waiting, and that will explain for sure CXPacket increasing over time and execution time is decreasing because, no, sorry, increasing as well. I mix it up. Increasing because of wait statistics, nothing else. So This doesn't work for OLAP, so reporting. We usually deal with column store indexes. This is, do I have the right table with me? Just want to check. Yes, that is the right table. So the CSI. This is a column store index table which have 500 million rows. So let me execute this with a max degree of parallelism of 1. And let's, oh sorry, I guess I forgot to enable the, no, statistics on. So I asked SQL Server to run this with one single thread. It will take roughly, I don't know, 5 up to 6 seconds. But we are dealing with much, much more data than in an OLTP system. So let me execute the same query, not limited by the CPU, and it will almost immediately, it is there within a second. I mean, it takes some time to display the grid and data visualization. So believe me, it's nothing else than almost 0 seconds. So that means column store index will definitely benefit from parallelism because of the batch mode. Batch mode will also definitely benefit from more than one concurrent threads. But this is again different for OLTP. So let us try to figure out what CXPacket is. CXPacket is named class exchange packet. A class exchange packet is, let me open Paint for you. I mean, I'm not a painter, but and even with a mouse it is a little bit harder. But let's consider the following. We have 4 threads. So this is a parallel execution of a query. So very likely you scan an index or whatever in the beginning, because when you have an index seek, it's very unlikely that you have a cost threshold or cost more than 5, because otherwise, I mean, you understand an index seek is definitely cheap. So let's say we scan an index, right? Because otherwise we will end up with a serial plan. And this time we have a parallel plan, so that means on the right-hand side we have a so-called page supplier. The page supplier isn't visible because, for whatever reason, I don't know, but the idea is that roughly 1/4 of the pages will be read from the first thread, the 2/4 of the number of pages which are available from the table will be read by the second, and so forth. Yeah, so it's some kind of a balanced. Yeah, it's never ever balanced, but this is already the problem. When something isn't balanced, there's always one thread which takes longer to do their work as another one. Let's say this will end here, this will end here, this will end up here, and this will end up here. So you can see already that the longest, the thread which takes the longest in order to satisfy the workload is nothing else than the execution time. It will determine the execution time, right? Because all the other threads have to wait. And there's a coordinator thread called 0, which takes care that all the work will be done or have been done from all the threads until the class exchange operator will pass the data into the next operator through the pipeline. Okay, so class exchange package will cover or will only measure the time your query will spend in parallelism. That is the time here, right? It is here, it is here, it is here. Yeah, okay, this was wrong. So this one, so it's never nothing else than the sum of the time the query takes in parallelism. Is this bad? Is this wrong? I have read a lot of articles telling me, okay, oh, CXPacket, you have to worry about it. No, I don't care, because I can, if I decide for a parallel plan, CXPacket only measures the time it takes to run in a parallel fashion, nothing else. I don't care. The only thing I can do is I can reduce the cost of the query in order to make sure that the query runs faster, CXPacket is less, or maybe we are even less or below the cost threshold for parallelism than we are running in a serial plan. That's all. Then CXPacket is gone because CXPacket is not there because the plan is not a parallel plan anymore. So let me go down. Let me do the following. I just want to make sure. I have 10 minutes, yeah, that's good. Okay, cool. Let me run this. So I set the cost threshold for parallelism to 5, the default. Yeah, otherwise I have to produce a workload or a query which is much, much more costly. But the result is the same. So, oh, sorry. Let me go to this query here. Okay, just want to get a new fresh session, which is 53. So the problem is the following. When I now execute a query like this, and I limited this to 1, SQL Server, as you know, cannot run a query in parallel. And this time I will change it to AdventureWorks, which makes much more sense. So it will take a while, but this is good because in the meanwhile I have time to evaluate what is going on. So from a session wait stat perspective, you can see currently there is no CXPacket. Why? Because the query is not running in parallel. Instead, we have a page IO ledge shared, which means SQL Server has to read all the data from the disk, because reading a page which isn't in the buffer yet causes page IO ledges, which is an indication that your disk is slower than the request. Yeah? Let's say it in this way. But there is no CXPacket for sure. So what we can see from an operator perspective is there's a nice is this the one? Let me check. Let me first of all execute this one. Yeah. So no, this is not the one. But still, we can see only one thread. One thread is allocated for this query. No parallel execution. And you can see that the request status is changing from time to time. And here we can see what is currently going on. So there's a nice DMV which is added, I think in 2019, which is exact query profiles, which give you an indication of the execution plan. You can see there's a sort, there's a table scan, and currently there's only one thread allocated to each of the operator. Let's do the same with another query, or with the same query, which isn't limited anymore. So this time it is again 53. This time we can see that query is waiting for CXPacket. That is the reason why it takes longer, right? And for sure it will increase over time. Yeah. So same as 53, number of threads. We have to have more than one, because otherwise the query would not run in parallel. We have 9 coordinator thread plus 8, because we don't have more than one branch. One branch multiplied with 8. Which means 8, but plus 1, which is the coordinator thread. And you can see the coordinator thread here. You can see that there is the thread 0, which is currently, when you look into the execution plan, you have to read it from the left to the right, from right to the left. Sorry, this is the same here. So we will start with a table scan. We end up with a sort, and in the end, everything the streams are gathered to display the result. You can see that thread 0 will span across all the work which is done in parallel. That is your coordinator thread. So, and underneath you have all the threads which are coordinated by the coordinator thread. That is the reason why you need to have more than one. Okay, we have 5 minutes left for thread pool starvation. That is nice. Thread pool starvation. Is this the one? Just want to check. Yeah, okay, cool. Hopefully it works. Sometimes it doesn't work. So maximum worker count is 128. So normally, or usually for my machine, depending on the number of cores, is 576. I already set it to 128 because I used the session before I presented this, or I went through the session another time to make sure that everything works. But usually this 576. So this time you can see that the maximum worker thread is set to 128. So I limited the number of worker threads in order to make sure that I do not need to produce a workload which is running in parallel more than, I don't know, 200 times, yeah, in order to get an exhausted worker thread pool. Yeah? So, but you can imagine that it's still the same. You have a limit. Currently it's 128. Maybe it's 576. Maybe it's 900. I didn't remember anymore, depending on the course. But you have a limit. Okay, let me do the following. I will set the cost threshold for parallelism to 5. And it is set to 5. Perfect. So when I execute this plan is single-threaded, and it has a estimated cost of 47. So usually this query would run in parallel. Let me see or display the execution plan. The execution plan looks like this. For sure, serial plan, one thread, which means when I have 128 threads available, how many executions of the same query I can do in parallel? Roughly 128. I mean, they are threads allocated to internal processes, but let's give it a try. So OStress is a tool which you should use whenever it comes to performance tuning. It is never ever just to tune one query, it's tuning a workload. So OStress is for free. You can download this as part of RML utilities. Microsoft renamed this one. I didn't remake database experience tools or whatever. I didn't remember the name anymore. It's just marketing. It's still the same tool. So that means in this case, I run the same query. You can see the query here, where we already know how the execution plan looks like, with a limit of one thread, 80 times at the same time. So n is the number of concurrent threads 2 times. Let me do this. So in the meanwhile, I will execute the thread allocation. It will take a moment because very busy. You can see that roughly 76, some of the queries were already done. 80 threads, 80 queries, all of them are running, no blocker, okay? We know 80 threads is less than 120 available maximum worker threads, so therefore no thread pool starvation. Okay, so we can see the same here. From a OS scheduler perspective, worker queue means, is there a queue or thread which is waiting before the scheduler, before an idle thread can pick up the work? Because we need to differentiate between work and threads. Yeah. So no problem, I can run it. So that's perfectly scaling as far as we are not reaching the limit. We can see that wait stats, there is no waiting task, there is no thread pool, there is no CXPacket. Finally, I can ask DMOS waitstat to get an aggregated view of thread pool and CXPacket. Oh, sorry, I forgot to reset it. Believe me, it should be 0. Yeah, I forgot to reset this one because you can imagine that when a query is not running in parallel, I cannot have CXPacket. Yeah, I forgot to reset the statistics, which I will do now. And I have 2 minutes left. That's perfect. So we will run another query, same query as before, but not limited. This time we can see that the query is running with more than one thread, to be precise with 8 threads plus 1, the coordinator thread. So let me reset another time. I'm pretty sure I did it already. Same query as before, not limited. So that means query can run in parallel. And now something completely different happens. So first of all, we should see that some of the queries are running, and you can see the requested DOP is set to 1. And now something which I figured out the first time in 2017 happens, or 19, I didn't remember anymore. The requested DOP is 8. But SQL Server is trying for some of the, you can see it here, some of the queries, exactly the same query. It's always the same query. You remember we are running the same query 80 times concurrently. Some of the queries will be reduced by just using 1. That means SQL Server Engine is very smart. Okay, it will detect a thread pool starvation already and try to reduce the requested DOP for all queries which are coming now. The problem is you get, okay, cool. Let's give it another try. So what you see here is a thread pool starvation. So you can see the work count, work queue count. That means because we are running in parallel 8 times, 80 times 8, so 80 times multiplied with 8 threads per query is definitely more than 128. That is why we have a so-called thread pool starvation. There is no idle thread anymore, so therefore the work queue count is showing that there are threads waiting for a scheduler for an idle task to pick up. So that is called a thread pool starvation. Very, very hard to detect. Very easy to resolve. How can we resolve it? I mean, first of all, let me do this. So here, this time, we should see CXPacket. How can we reduce this or eliminate this completely? Make sure that the query is cheaper than the cost threshold for parallelism, because then query cannot run in parallel. So what can we do? We can increase cost threshold for parallelism. It's not a good idea because it works for all queries. What is much better to introduce a better index. Because if I have an index, then I'm not ending up with a hash join. Instead, I will end up with, you can see it here, reduce cost. Yeah? So I can create a non-clustered index with all the columns which are included. So therefore, SQL Server can have an index seek instead. Cost is down to 1. So therefore, I don't have parallel queries anymore. Therefore, I'm not running in a thread pool starvation. That is how to fix it. Because again, cost threshold for parallelism on an instance level means every single query will now run either in a parallel or in a serial plan because you are changing the setting. That is too dangerous. Make sure that your query is cheap to avoid thread pool starvation. That's it. Yeah, stop. I can see the hint. Okay, cool. Any question from the audience? Okay, cool. Any question from the audience here? I'm still here, okay? Okay, I will be here for 10 minutes if you want to. Thank you.